What if I told you that the particle could exist in two states at once, and the mathematics is the language that explains it? Welcome to Maths for Quantum Computing, your visual journey into mathematical foundation of quantum world. Quantum computing isn't just about strange physics. It's built on precise, concise, elegant math that describes how qubits behave, evolve, and interact. In this video, we'll break down the essential mathematical tools that every quantum developer, researcher, or enthusiast needs to understand. No overwhelming equations, just clear visuals, core concepts, and practical intuition. Here's what you'll learn today. Linear algebra and Dirac notations. The building blocks, vectors, matrices, and inner products. The elegant Bra-Ket notation for quantum mechanics. Quantum states and global phase. How qubits are expressed and normalized. The Bloch sphere and rotations. Visualizing qubits geometrically, moving qubits with precision. Measurement and observable. How we extract information from a quantum system. Superposition and interference, the phenomena that gives quantum computers their power. Tensor product and multi-qubit product systems, scaling up to multi-qubit states and entanglement. Quantum operators and eigenvalues, predicting measurement outcomes mathematically. We begin with linear algebra, the language of quantum mechanics. A vector like ket v equals column vector of AB and the inner product read as Bra v ket of W. We'll calculate what is inner product of V and W, where V is A1, B1, ket W is A2, B2. Here we need to write the Bra notation of V. So it will be transpose of ket notation and ket of W will be A2, B2. So the inner product will be A1, A2 plus B1, B2. The norm of vector written as double bar V double bar. Given its length, the quantum state must be norm equals to 1. Matrices act on vectors. Apply a matrix A on ket V. We'll have a new ket W. Unitary matrices are important in quantum computing because they preserve norm. Hermitian matrices are used to represent physical observables like energy or spin. Now, moving on to Dirac notations. We have ket notation and Bra notation. In quantum computing, we use Dirac notations. Ket psi, let's say, is a column vector. Its conjugate transposes bra psi. The inner product bra psi ket phi gives a scalar, and outer product gives a matrix, often used to construct operators. The projector like ket psi bra psi helps us model quantum measurements. The completeness relation says that the sum over all outer products of basic vectors equal the identity matrix. This tells us basis spans the full space. A single qubit is written as ket psi equals to alpha ket 0 and plus beta ket 1, linear combination of basis states. Here, ket 0 and ket 1 are standard basis states. The normalization condition says that the sum of squared magnitudes of alpha and beta must be equals to 1. This ensures that the probabilities add up correctly. States like ket plus and ket minus represent equal superpositions. Also, global phase multiplying by a complex factor like e to the I theta has no effect on measurement outcomes. Now let's see how qubits are represented in form of matrix. First we have ket notation, that is Dirac notation. Ket 0 is basis state representing 0. Ket 1 is basis state representing 1. Ket 0 is represented as 1 0 and ket 1 as 0 1. We have seen here vector form and we have four conditions to satisfy a quantum state: orthogonality, normalization, inner product, and outer product. Firstly, let's see orthogonality. Two vectors are orthogonal if their dot product is 0. We have 0 and 1 which are orthogonal. So let's compute the inner product of bra 0 ket 1. 0 is represented as draw 0 is represented as 1 0 and get 1 is as 0 1. So after doing inner product, we'll have to multiply the draw 0 and get 1. We'll get 0. So 0 1 are orthogonal. So for vectors to be orthogonal, the dot product must be 0. If we take the same vectors, let's say we have parallel vectors. So draw 0 and get 0. When we multiply them, we'll get a value of 1. So these are parallel. Now let's see normalization. Each and every quantum state must be normalized. Let's take ket of 0, normalize them. We know the ket of 0 value is 1, 0. So normalizing is taking the coefficients and squaring them. We'll have the value as 1. Here also taking 1, that is 0, 1, normalizing it, we'll get 1. So sum of squares of amplitude should be 1 for every quantum state. This satisfies in ket 0 and ket 1 in any other non-quantum state also. Now let's see about inner product. It is also known as Bra-Ket notation. Measures similarity or overlap between two quantum states. Let's say A and B are quantum states. Then inner product is Bra-A ket B. This measures the similarity. It's like dot product in linear algebra, giving the projection of one state onto the another. Let's take ket of alpha, ket of beta, be these two vectors, and we are performing a inner product. So this will be transformed and this will be multiplied. So we'll get a value as 1 over root 2. Now outer product. The outer product creates a matrix or linear operator from two vectors, one in column form and one in row form. First ket of A and then row of B. It represents a projection operator onto the B. Building density matrix, use cases, projecting quantum states. Let's say example, this is ket A and row B. When we perform an outer product, we'll get a matrix 4 by 4 with this value. To visualize a qubit, we use Bloch sphere. Every pure state corresponds to a point on the surface of its unit sphere. We can write the qubit as ket psi equals to cos theta by 2 ket 0 plus e power I beta sin theta by 2 ket 1. Here the coordinates are x, that is sin theta cos beta, and y sin theta sin beta, and z is cos theta. Here the pure states are nothing but the surface of sphere. This representation is powerful because it lets us picture quantum states and their evolution geometrically. Now let's see about state rotations. We have Pauli matrices and rotation gates. To manipulate quantum states, we apply rotation gates. Pauli matrices X, Y, and Z define the axis of rotation of the Bloch sphere. We then define rotation operators. Xy of Rx of theta rotates around x-axis, Ry of theta around y, Rz of theta around z. These gates are key components in quantum circuits, letting us move states around the Bloch sphere. Let's see how Pauli gates makes the qubit move in Bloch sphere. Firstly, let's see about Pauli X gate. Pauli X gate performs a rotation of pi radians, that is 180 degrees, about x-axis of the Bloch sphere. It flips the qubit between ket 0 and ket 1, effectively acting like a quantum NOT gate. Coming to Pauli Y gate. Pauli Y gate rotates the qubit 180 degrees about the y-axis of the Bloch sphere. This not only flips the state but also introduces a complex phase causing movement through both real and imaginary axes. Coming through Pauli Z gate. Pauli Z gate rotates the qubit 180 degrees but about the z-axis, leaving the computational basis states like ket 0 and ket 1 unchanged. It flips the phase of ket 1, causing a change in relative phase while keeping the qubit on the same vertical axis. Superposition allows a qubit to exist in combination of states. Ket psi equals to alpha of ket 0 plus beta of ket 1. The Hadamard gate states equal superpositions. Let's say we are applying Hadamard on ket 0. The result will be ket of plus. If we are applying Hadamard gate on ket 1, we'll get ket minus. When the quantum states interfere, their amplitudes combine. This can result in constructive or destructive interference. Powering algorithms like Grover's and Shor's is used through interference. This is also key to quantum parallelism, evaluating multiple possibilities at once. Now let's see about tensor products and multi-qubits. In quantum computing, we build larger quantum systems using tensor products. Tensor, tensoring ket psi and ket phi creates a composite state. For instance, ket 0 tensor ket 0 gives us ket double 0. Represented as four-dimensional vector, you can see here. Some multi-qubit states like ket plus equals 1 over square root of 2 times the sum of ket 0, 0 plus ket 1, 1 are entangled. This means they can't be separated into individual qubit states. And it's what gives quantum computing its real power. Let's now explore a foundation concept, quantum operators and eigenvalues. In quantum mechanics, observables like energy, position, or spin are represented by Hermitian operators. These are special matrices that are equal to their own conjugate transpose. The key equation here is the eigenvalue equation. Here, A acting on ket psi equals to lambda times ket psi. Here, ket psi is eigenstate and lambda is eigenvalue, which is the actual value you get when you measure the system. For example, Pauli Z operator acting on ket 0 gives plus 1 times ket 0. So plus 1 is the eigenvalue for that state. Similarly, ket 1 is eigenstate with eigenvalue minus 1 under Z. But Z isn't the only operator. The Pauli X operator has its own eigenstates. Ket plus has eigenvalue plus 1, ket minus has eigenvalue minus 1. When you measure a quantum system, the state collapses onto one of the eigenstates of the operator, and the measured value is the corresponding eigenvalue. There are some important properties of Hermitian operators. Their eigenvalues are always real, eigenstates are orthogonal, they can be diagonalized, which makes them easy to work within quantum algorithms. Finally, the measurement basis is nothing but set of eigenvectors of the observable. That's why we often talk about measuring in the z basis, x basis, or any other eigenbasis. Let's wrap up with a complete picture of what we have covered in this foundational journey through quantum math. We began with linear algebra, how vectors, matrices, and inner products build the structure of quantum mechanics. Then we introduced Dirac notations, where Kets and Bros gave us a clean, powerful way to express quantum states and operations. We examined quantum states as superpositions of basis states and saw how the global phase levels probabilities and changed. Using the Bloch sphere, we have visualized quantum geometrically, qubits geometrically, and saw how Pauli matrices and rotational gates move qubits across the space. In this section on measurement, we have learned that quantum outcomes are probabilistic and observables are represented by Hermitian operators with each result tied to an eigenvalue. Through superposition and interference, we have explored how quantum states can combine and amplify, enabling parallelism that classical systems can't match. Then came entanglement, where we used tensor products to build multi-qubit systems that can't be separated into individual parts, a unique quantum resource. Finally, we've studied about quantum operators and eigenvalues, where measuring a state reveals an eigenvalue and the state collapses into corresponding eigenvector. All these mathematical tools are more than theory. They are foundations of quantum gates, circuits, and algorithms.
Subscribe for more quantum computing videos.